Okay, welcome back for another episode of Con E 352. We are going to continue our discussion of cooling and cooling calculations, and we're going to start discussing the process of air conditioning. Air conditioning is the purpose of air conditioning is to remove both sensible and latent energy out of the airstream. Now, what we did before is we calculated the space sensible load, all right? All of the sensible heat loss. And remember the definition of sensible heat loss. Sensible heat loss is just the heat loss that results in a difference in temperature of air. It doesn't take into account any of the moisture that is in that air. It's just the same energy like sensible heat production. An example of that would be a simple electric space heater. It changes the temperature of the air, but it doesn't add or subtract any moisture from that air, right? So that is a pure sensible heat gain. And then to offset that, we would need to remove sensible energy from the air. In other words, cool it back down. Well, we all know that, especially here in Iowa, it's more complicated than just looking at sensible energy. So far, all we've done is discuss sensible. Now we're going to discuss removing both sensible energy and latent energy. In other words, I've got to cool that air down, and I also have to dry it out a little bit. I've got to remove some moisture. So here we're going to use, in a little bit, we're going to use something called a psychrometric chart. But here, first what I want to do is give you a little preview of the class today and also what you're going to need because it'll help make this lecture better. First, I'm going to start with page 29 of the lecture notes. It's that just like a Word file that one of my students typed up earlier. It's just the lecture notes kind of presented in the way I did it that semester that he typed them up. There's also going to be a PowerPoint file called Psychrometrics. It's HVAC PowerPoint number 5. And then you're also going to need a psychrometric chart. Now, a psychrometric chart, it is just a chart that shows us all the possible combinations of temperature and moisture levels and the resultant energy in that air at, and this is important, at 1 atmosphere. Barometric pressure is about 29.9 inches of mercury. Once again, remember, in this class, I joked about using the metric system before, and the reason I joke about that is in HVAC, we use a lot of very weird English units. All right, inches of mercury, that's actually a pressure reading. Inches of mercury, in other words, if I had a complete vacuum on one side of a straw and the pressure in the air on the other side, it would offset 29 inches of mercury in that straw. That is 1 standard atmosphere. That probably translates to something in pascals or newtons per square meter, but the thing is, I don't care. We're going to use inches of mercury, but we're only going to use that one atmosphere. If you ever take any classes on, say, turbine design or air compressor design, you will use a chart like this, but the pressure will change. For HVAC systems, doesn't change that much. So we're only going to use a chart at 1 atmosphere. If I suggest you use this one, it just says chart.pdf on the Canvas site. I suggest that you use that one. There's others out there. The reason I like this one is that the temperature along the bottom here goes a lot longer range than some of the others that you could read out. This will be easiest to read if you print it on an 11 by 17 paper, and also make doing your homework easier. So I suggest you get this one, print it out. If you download one off the internet, and this is the important part, if you download one off the internet, make sure that the barometric pressure is either, it says like 1 atmosphere or 29.9 inches of mercury, or whatever that translates to in kilograms per square acre. I don't know. Okay, it's got to be at 1 atmosphere. All right, 1 atmosphere. So get those things out, pause if you need to, and then come back, and we're going to continue our discussion. Air conditioning. All right. 2 equations that you're going to need here. The first one we've already seen, 1.08 CFM delta T. Anytime I have air at 2 different temperatures and they mix like they would in a room, if I'm heating that room up and I'm supplying hot air to the room that went through a furnace, I'm going to add energy. If I'm cooling it down, if I'm wanting to air condition, and I'm going to throw cold air into the room to offset the heat gain, right? That removes energy. This is the equation. 2 different airstreams at different temperatures, and we use that equation. The next one is one that we haven't talked about yet. Latent energy transfer. 0.68 times CFM times the difference of grains. Here's another example of one of the weird English units. Grains. Remember, a grain is something very, very small. It is 1/7,000th of a pound. Why do we use grains? Because everyone does. Kind of like how each of these, Q sensible and Q latent, are in British thermal units per hour. And once again, I'm going to point out the observed. Not even the British use the term British thermal units anymore. But we do, because we're stubborn. All right, and that's just the industry and the way it is. So we're going to calculate the rate of heat transfer, both sensible and latent. If I'm air conditioning, I've got to remove both of those, and those represent a heat transfer. So that once we calculate this, we'll be able to size our air conditioning system. Notice this first one, all right, the 1.08 CFM delta T. Think about it like, so we calculate all the space loads, and I'm going to dump cool air into that room from an air conditioner to offset all of that heat gain. We are trying to keep our space at equilibrium. In other words, that 72 degrees that we said that's the desired space temperature, that is abnormal. It's not natural for a space to stay 72 degrees year-round. In Iowa, we'll have 72 degree weather outside about 3 hours in the fall and 3 hours in the spring. Well, okay, maybe it's more than 3 hours, but it's not much more. So trying to keep it at that perfect 72 degrees is unnatural. It is an abnormal condition, and we are trying to add the right amount of cool air or hot air to the room to make it stay that way. So notice this though. If our temperature, if the delta T here, the 1.08 CFM delta T, if that changes, in other words, if the space is at one temperature and we make the supply air temperature colder, if the heat gain is a constant for a little bit, I can supply fewer cubic feet per minute of air at a cooler temperature to keep the room 72 degrees. Think about the ductwork systems in a large building. Think about how important this is. It's like, so the colder the air is that we dump into that room from the air conditioning system, the less air will have to move, which means the smaller the ductwork could be to get that same heat transfer. That's a pretty important deal. Less fan energy, all right? Less air moving around the building. Downsizing ductwork, saving money on the ductwork, and probably more important, saving space in the overhead. Now, there's a problem. Too cold of air, we can't just make that air colder and colder, or we'll run into problems. Too cold of air may result in condensation. In other words, if the air coming out of the diffusers in any individual room, if it's too cold, they might start to drip, especially when it's really humid out, or when it's really humid in the room. All right. Also, if you're right below one of those diffusers and you have super cool air coming out, too cold of air, and it'll be really cold right where that air is blowing, and then it might not get enough circulation to keep the entire room at an even temperature. You might get it kind of spotty, where it's really cold in a spot and a little bit warmer in other spots. Most of the time, here, this supply air equals 50 to 55 degrees Fahrenheit. That is the supply air temperature for most of the air conditioning systems that you're going to come across. Probably has a supply air temperature in the range of 50 to 55. That's just common. What it does is it allows it as cool as possible before you start having some of those condensation problems. Okay. Now, something to keep in mind. We can use this equation, this 1.08 CFM delta T. As an engineer, I can use that in a couple of ways. If this was an existing building and I wanted to know, well, what is the maximum cooling capacity? In other words, what's the maximum amount of heat production in a room I could have? And I'm talking about the maximum of people and computers and lights and everything. I could measure the supply air CFM, measure the delta T. In other words, if the space is at 72 and my supply air is 55, I could calculate the maximum load that could occur in that room and still be able to keep it at 72 degrees. That's like a remodel question. I've got this room. Let's say I want to turn it from an office space to a computer lab. Well, how many computers and how much heat production could I have based on existing equipment? All right. So measure CFM, measure delta T, and then calculate the maximum heat gain that's possible. If we are designing it from new, in other words, the building isn't built yet, I'm a design engineer and I'm going to design the mechanical systems, I'm going to choose the delta T. In other words, that is an engineer's choice. The engineer is going to pick, what is my space temperature? The engineer is going to pick, what equipment are we going to buy and what is the supply air temperature of the equipment that we're going to purchase? And then we're going to calculate what I think the space sensible load is. And then we're going to calculate what is the supply air CFM. In other words, how much air does that air conditioning system need to provide based on all those other assumptions? So there's a couple different ways that we can approach these equations. And in this class, I'll probably have you do both at one time or another, whether it's test problems or homework assignments, that type of thing. All right, let's scroll on down. Here's that example. Here's a computer room. Right? Anytime that you change the occupancy or use of a room, you need to go through, or rather, you should go through this calculation to make sure that you haven't modified the room in a way that the air conditioning system can't accommodate. All right. So let's get into this idea of psychrometrics. Now, notice, it's spelled wrong here in this Word file. It's actually right on here, psychrometric chart. The thing is, spell check does not like psychrometrics. And anytime you just type it, it'll probably give you an error message or flip back to psychometrics. Right? So I apologize. It's going to be spelt wrong, and that's spell check or autocorrect hitting that for us. All right, this is the chart that I had you download, this one. This is just the simplified version. Here is that curve, all right? This chart represents all the possible combinations of dry bulb temperature here on the bottom. The axis that goes on the bottom is dry bulb temperature. The axis on the right is humidity ratio, grains of moisture per pound of dry air. These curved lines are percent relative humidity. Now, doesn't go on forever. It ends here at the 100% curve or saturation temperature. In other words, this is it. This represents 100% saturated. The air cannot hold any more moisture. Think of that line as the point at which we start to get rain or fog. All right, now there's some more lines on here, but let me just start. This curve is what we will use to calculate the total change in energy as we go through a cooling coil. All right, the total air conditioning load. All right, couple of terms that we've already talked about, but I want to stress, if we go all the way out to the right on this, we'll look at this in just a second, but there's other information out here, not just humidity ratio and grains of moisture, but there's also going to list like dew point temperature and vapor pressure. Right? Those are all things that are also on the chart. If we flip over to the chart, okay, that's what these are right here. Humidity ratio, grains of moisture, and then right here is dew point temperature, and then this is vapor pressure. So if you know any two characteristics of air, we could say, oh, hey, it's 80 degrees today, and it is 50% relative humidity. Right? Here's the relative humidity lines. Those are the curves. You could plot that and then look up all these other values. We're going to do that here in just a second. So if you don't have a copy of this printed out, go ahead and print it out. Get yourself a ruler and a pencil, and we're going to do a couple of exercises on this. All right, notice. Here, I'll give, let's see here. I want you to look up a couple of values. We'll come back to this in just a second. On this chart, go ahead and look up, all right, plot this, 95 degrees Fahrenheit in dry bulb temperature. That's this line across the bottom. And then go to right here. This is 78 degrees wet bulb temperature. If you look closely, you'll see the temperatures right here that go along the curve, and then some kind of lines at an angle. Some of those lines are the wet bulb temperature. So if I can read if I walk outside, I've got a thermometer and a wet bulb temperature sensor, I can get those two values. I could also look up, I could find what the relative humidity is outside. If we just check the weather conditions outside, we can get temperature, dry bulb temperature, and maybe a humidity. And then I could look up all the other values. What I want you to do is just do that, all right? If we look at 95 degrees Fahrenheit, 78 degrees wet bulb, go ahead and plot that, right? Take your pencil and just plot that. 95 is right here, and go up to this point right there. 75, 76, 77, 78, 79, 80. So 78 is right here. It's this line that goes down like this. And when we plot those two together, now you can read all the other conditions. You could come over here and read humidity ratio in grains of moisture per pound of dry air. We can go a little bit further and read dew point temperature right here. And if we look at 9578, and I'm gonna blow that up just a little bit. All right. 95. Okay. 78. It's right there. And if we pull that out to the side, you're going to find a humidity ratio of right about, let's see here. I believe it's right about 100 and 16 or so grains of moisture, right? I obviously I'm just using my finger on a screen, so I'm not exact on that, but I want you to look at it exactly. Go out there and find the humidity ratio in grains, and then you can also find the dew point temperature. All right, the dew point temperature, if it's like 116, is going to be right around 72 degrees, real close. And it's important to understand that. And it's not like that's all that unusual of a condition for Iowa. What that means is that our design outdoor temperature, the dew point of that air is going to be at or above the temperature of the building inside, our inside condition. And that is an important thing to realize, because what that means is your entire building is below the dew point of the outside air. Everywhere you get infiltration, you are going to have condensation. It is just a fact, right? It is just a fact. When you get dew points that are at 72 degrees and higher, and wouldn't be uncommon in Iowa to have a dew point of 75 degrees, 76 degrees. Everywhere where air sneaks into the building, it is going to have condensation, and that is a pretty big problem. That is why we need vapor barriers that are intact and placed in the right spots in our walls. As that outside air comes in, if it was allowed to come all the way into the building, it would ultimately condense, and therefore we would guarantee ourselves problems. All right? We just guarantee ourselves problems. So just know that, here we go. Let's see here. So just know that is why knowing where the point of condensation is very important on our building profile, and putting that vapor barrier in the right spot in our building profile is so important that we prevent condensation and mold. All right, a couple of more equations. Anytime that we use that psychrometric chart, we can use it to find the total energy change from one condition to another. Here, this is graphically representing those two equations that I gave you earlier. Let's say that we have a mixed air condition, or just a room condition, and a space condition. As I cool that air down, I will lose both sensible energy and latent energy, and I can plot those on that chart, use these equations, and come up with the total energy change. Note on this chart, we can also look up the difference in enthalpy on the chart. The difference in enthalpy from one point to another is essentially the sum of sensible and latent energy. Think of enthalpy as the total energy in a system, in this case our system being moist air. If we go back to our psychrometric chart, and I'm going to zoom out a little bit. Look over here on the right. These lines are enthalpy lines. Notice these go down. They're not quite parallel to wet bulb. They are really close, but be cautious. They are not quite parallel to wet bulb lines. But this is the enthalpy, BTU of energy per pound of dry air. Pretend for a second I could catch a pound of dry air and then measure the total energy in there. There is a latent component, which is the moisture in the air, and there's the sensible component. There is the temperature of that air. If I was able to add that together, that is an expression of BTU per pound, which is enthalpy, the total energy of any air. Back to, here we go. So I can use this equation, new equation, write this down. You need all three of these. These are three key equations as we're using the psychrometric chart and calculating air conditioning loads. Sensible, latent, and then adding those together is total. There's another equation. 4.5 times CFM times the difference in enthalpy. 4.5, just like the 1.08 and just like the 0.68, those are all merely constants that make all the units work out. Cubic feet per minute times grains does not equal BTU per hour, right? The 0.68 works that equation out. It's a constant that makes the math work. Same way with 1.08 CFM times the difference in temperature. Same with 4.5 times CFM times enthalpy, which is in BTU per hour per pound of dry air, right? So those are all constants. Anytime that I give you two different psychrometric state points, you use these equations to determine the difference in energy between those points. How are we going to use this? All right. Here is my diagram that, like I said, you're going to see 100 times in this class. I have a building, and I want to keep this at 72 degrees. It's hot outside, okay? We are going to return air, cool it, and then supply it again. This air is now colder than the air the air coming into the room through the diffusers and the registers is cooler than the air that we're pulling out of that room. If I'm going to offset all the heat gain from heat conduction, the solar part through the windows, heat produced by people and lights and computers, if I'm going to offset all of that heat gain, I have to supply air that is colder. I can use those equations to calculate these values. The way we start this, the design process. First, we'll calculate all those space heat gains. That was the last part. That was last week's. We add up all the sensible space loads. Now, and this is why we only looked at sensible space loads. In terms of kind of real world practicality, at the room level, most of the load is sensible. In other words, we don't have a lot of moisture production. There's only two sources of moisture production in like an office space or a classroom. Latent energy produced by people, and then latent energy that's coming in through infiltration. Compared to the rest of the loads, lights, conduction, solar, radiation from people, and lights and infiltration, compared to the sensible heat gain, the latent is fairly small. Changes a little bit when we bring in some outside air from the outside in summer, but for the room, for the space level, the loads are mostly sensible. Also, the device that we use to control whether or not we need air, cool air, and how much of it is just a thermostat that's going to be sitting on the wall. Think of your house, think of your car, think of an office space. You've got a thermostat on the wall. It's going to measure the temperature and then decide, hey, do we need air conditioning or not? And if we do, we're going to dump some cool air into the room. That sensor is a dry bulb sensor. We do not have moisture sensors in each room. And here's why. It's just kind of a practical thing. One, if the latent loads are fairly small compared to sensible, maybe it's not as necessary. That's part one. Part two, humans are pretty sensitive to changes in temperature, but it takes a fairly large difference in humidity before a human will even know. In other words, we're just not going to notice it that much. All right? And then part three of this. To be able to change the moisture level in each room in a building is a very difficult and expensive process. You'd have to be able to remove moisture or add it as needed. Given that it's a small value compared to sensible, and given that people aren't near susceptible to changes in it, it doesn't make practical sense. So we are going to base the amount of supply air, the CFM of supply air into a room, We're going to control it based on space dry bulb temperature, and we're going to calculate it based on sensible only loads. Right? Now, once we return that air, we're going to exhaust some of it and bring in some outside air. Remember, the amount of air that we're going to bring in is based on ASHRAE Standard 62. There's that table that I handed out. It's one of the tables in the handout packet that we looked at earlier. That'll tell you how many CFM per person that we need. Once we get there, that is going to, after we exhaust some of the room air and replace it with hot and humid outside air, now that is going to represent a fairly large increase in humidity. And now we need to take into account the coil load. That is the total difference in energy as we go from the mixed air condition, the return air mixed with outside air, across the coil and make it into supply air. The total amount of energy that we have to remove is the air conditioning load, the total coil load. The coil load is different from the space load by the amount of ventilation that we have to provide. Right? So with that idea in mind, we're gonna go to a Psych Chart example here. How to read the Psych Chart, right? When you are plotting points, I want you to plot them, circle them, label them. Most of the time, let's just start from left to right. Most of the time, the supply air is an engineer's choice. For this class, we're going to use, a lot of times we're going to use 55 degree dry bulb, 53 degree wet bulb. Just a little bit drier. In other words, not on the saturated line. I don't want to supply air to a space that's already at saturation. It'll just be just a little drier. This return air point, well, this is just the space condition. The difference between the two is our total space load. Notice, most of that is sensible, and there's just a little bitty bit of latent. Right? We only calculate the sensible load, though. Now, outside air. Let's go back to this picture. So that's the air that we dump into the room. The air that we return is the conditions that we want the space at. In other words, 72 degrees Fahrenheit, 50% relative humidity. Most of the time, those are the space conditions that we're going to use for this class. Outside air. So we're going to exhaust some of that air and bring in some fresh air into the air handler. Why do we need fresh air? Right? What's the importance of that? Well, everybody is going to be exhaling carbon dioxide. I need to get that out of there. Too high of carbon dioxide levels, and people tend to get drowsy, a little bit sleepy. Starts to smell a little stale, if you will. Not only do people produce sensible energy, they produce latent energy, sweat, a little bit of evaporation off their skin. There's also odors. There's odors from off-gassing from carpets and furniture and paint and construction materials. There's odors from restrooms, cleaning products, copy machines, printing machines. All of those are going to produce odors, smells, and fumes. So we are going to exhaust all of that. Back to this right here. After we exhaust some of that and bring in some outside air, we are going to have what's called mixed air. I'm going to mix the return air with the outside air. What happens here? Well, we get the mixed air is in summer when it's hot outside. That's going to cause the return air to get hotter. Not as hot as the outside air, but somewhere in between that warm and humid outside air and that conditioned 72 degrees return air. It's going to be between there somewhere. And that's what this point is. If this outside air point is 95 degrees, 78 degrees wet bulb, the mixed air is a mixture of the two. In other words, somewhere on the line that we're going to plot between return air and outside air, this mixed air is where we're going to be in terms of conditions. Warmer and more humid than the space, but not as bad as the outside air. Where this mixed air falls on this line is a function of the percentage of outside air. In other words, we're going to calculate it. What is our total CFM? And then what is our outside air CFM? In other words, if it's 25% outside air, 75% return air, this point is only 25% of the way from the return air point. If it was an even 50-50 return air and outside air, it'd be right exactly in the middle. And then let's say that it was 90% outside air, like you might see in a hospital or a laboratory. That could be all the way up here to 90%. The easy way to find this point, and write this down, right? Or just do this as an example. You plot your return air, plot your outside air. Draw a straight line with a ruler in between the two. Next, you calculate your outside air percentage. All right, let's say it's 20%. Your mixed air point is going to be 1/5, 20%, 1/5 of the way from the return air point to the outside air point. Probably the easiest way to do that is on the bottom sensible temperature line, subtract outside air from return air. In the examples that I've used so far, that is 23 degrees. If it's 95 degrees outside, 72 degrees inside, that is a 23 degree delta T. You take, of that 23 degrees, if it was 20% outside air, that is 20% of 23, and that is exactly 4.6 degrees. So to the return air, we will add 4.6 degrees, and that will make it at 76.6 degrees and go straight up to this line, and you have your mixed air point, and you can look up all the rest of the properties. All right. Couple of other things that I want to mention. Okay. When we're sizing our air conditioning unit, in other words, we're going to calculate this total load going from mixed air to supply air. This is the total amount of energy that we are going to have to, from this enthalpy point to this enthalpy point. That is the total amount of energy that our air conditioner has to remove. We don't want to oversize our air conditioning units, though. Just as a warning. It's okay to oversize heating systems. It's not okay to oversize air conditioning systems. Air conditioning systems, if you have too large of an air conditioner, it'll sit there and turn on and off and on and off, something called short cycling. And you will substantially reduce the life expectancy of that air conditioning unit. You will also not get really good humidity control of your space. And I'll kind of illustrate that with a few examples here later. All right, case studies. All right, we're at the case studies. Okay, hold on. I think I'm probably going to do a different video on case studies on Wednesday. But first, switch over to the psychrometric chart, right? The lecture notes, right? And also have this handout handy. This will just make more sense if we have both of these together. I summarized all the stuff that I just put out there on that I just went through in the lecture notes. It's kind of summarized here in the PowerPoint, right? The vertical lines, the dry bulb temperature. That's here along the bottom going straight up and down, dry bulb temperature. Horizontal lines are absolute humidity in grains of moisture. Right, go all the way out here. There's that humidity ratio, or absolute humidity, grains of moisture per pound of dry air. Relative humidity are the curved lines, right? They go from here all the way up here. And you can see that, 10%, 15, 20, 25 on up. And then obviously this line where everything ends is the saturation curve. That is 100% relative humidity. And then the dew point, also all the way out here to the far right, dew point in degrees Fahrenheit. Notice something even further out here that we haven't really discussed. This idea of vapor pressure. Vapor pressure. Here's something I just want you to think about. We're not going to use this vapor pressure point. But here I think for the next lecture, I'm going to do a couple of examples. And we're going to come back to this idea of vapor pressure. Think of the way I want you to think of this is water always runs downhill. And I don't just mean in terms of elevation. It always runs downhill. But if it's in a gas form, it goes from higher concentration to lower concentration. And in a building, if a building is cool and dry compared to the hot, humid outside, water vapor will migrate from the outside to the inside simply because vapor pressure is going to force it that direction. You don't have to have like wind-blown water on the surface of a building to get water inside. The vapor pressure will push it into the center of your building. And as we learned in 241, a lot of our building materials are porous, like brick and block. Brick and block, without a vapor barrier, is guaranteed to allow water vapor in when it's hot and humid outside. All right, we're going to come back to that. Like I said, I got a couple of examples to look at here later. Here's just the important calculations and the important equations. All right, I would expect everybody to know these. If on your handouts, you might even just want to write these out and highlight them on your handouts so that you have them, because we're going to manipulate these constantly in this class. All right, and then some important points, okay? Like I said, for Iowa, assume the outside air temperature is 95 degrees Fahrenheit dry bulb, 78 wet bulb. Typical design office and classroom spaces, 72 degrees dry bulb, 50% relative humidity. Supply air is typically between 50 and 55 degrees Fahrenheit. And supply air is a designer's choice. In other words, we pick what equipment we're going to buy. This supply air must be cooler and drier than the space. So just note, if you don't have to have 72 degrees dry bulb, 50% relative humidity, if you could get away with a warmer and more humid condition, you could get away with a warmer and more humid supply air condition. All right. And usually the difference between wet bulb and dry bulb temperature on supply air is about 3 degrees. All right. I'm going to assign a homework, HVAC homework number 4. I'm going to put it on the website later today, and then it'll be due on Monday. Please, please, please make an attempt at it and let me know if you have questions. And just a note, please don't wait until the very last minute for your questions. I just might not be able to get to them. If you're asking questions and it's 6 o'clock on a Wednesday, I'm probably not going to be able to answer them, even if they're due on Thursday. So the sooner I give you a week for this, so that my intent is that you'll try it right away and ask some questions. So start there. All right. So I'm going to assign the homework on Monday, but just keep a note, or due for Monday, but just note, I'm going to go over some more information on the Wednesday lecture that you'll probably need to complete all of that homework. So stand by for more examples and more discussions on psychrometrics. All right, let's begin another session of Connie 352. And what I want to do is I want to go over a couple of examples on the Psych Chart. And trust me, I understand that reading the Psych Chart is a pretty complicated thing the first time you try. You look at this chart and it makes absolutely no sense, or at least it doesn't seem to. There's tons of numbers, tons of curves, tons of axes to look at. And in all honesty, when I graduated from Iowa State a couple of years ago, we didn't have this particular class, Connie 352, and the only class I took on this was ME 441 and ME 442. And when I left those classes, I had no idea how to use a Psych Chart. So what I normally try to do when we're doing this live is go through a few examples and kind of get you to use the chart and help you to find different things. So my plan for this week is, first, I'm going to do a few examples here, just like single points that you have to find. Tomorrow, I'm going to make a video and go over some real-world examples, some case studies that I think will also help. But for sure, if you have problems, all right, you got to ask, okay? The discussion page is a good place to start. And if you're asking a question and it can't be handled on the discussion page, we'll do like a Zoom meeting or something, and I might even record it so that I can post it for everyone else. I won't record it without your permission, but just know that it's okay to ask for help on this. All right, so let's just go over the basics again. But first, before we do this, if you don't have a paper copy of the Psych Chart, please stop this and print one out. Preferably print it out like 11 by 17 if you can. You need something big. All right. Oh, hold on a second. That is not the view that I wanted. Okay. Okay, so let's. Not that big of a zoom in. All right, let's start. Here's the basics. If this is your Psych Chart, these are the basic axes. We went over this before, but this is here for you to review. Dry bulb temperature on the bottom, humidity ratio on the right axis. Past that is dew point, and past that is vapor pressure. On here, you can get dew point either by going out to that axis, or from your point move straight to the left to the saturation curve. That is dew point as well. So that is a straight line across there. It gives you dew point. Enthalpy are those axes all the way out to the top left. If you forget where this stuff is, come back to this graph. This next one. This is meant to kind of let you see, starting at any point, helping you move on this point to understand what's happening. If you are just moving to the right, that is only sensible heat. Move straight to the left, that is sensible cooling. Sensible heating and sensible cooling. We did not change any moisture. Right? Going down is dehumidifying and going up is humidifying. In other words, we're not changing temperature, we're just adding moisture or removing moisture. Down and right, chemical dehumidifying. I am not going to talk about that in this class, so don't even worry about that one. Evaporative cooling. Evaporative cooling. Think of that as like those misters that you see on the sidelines of football games when they're blowing out water and that water evaporates immediately and it cools you down. That is evaporative cooling. Up and right, that's if we're heating and humidifying, like a steam humidifier. And then down and left, cooling and dehumidifying. However, something important to note is that you cannot do this directly, this line that goes down and to the left. First, you have to cool it down to the saturation line, and then you drop moisture, right? So this has to happen in two parts. First, sensible cooling, and then sensible cooling and dehumidifying. All right, so that's how you're going to move around on this chart. Next, grab that psych chart. And what I did here, and I'm going to zoom in just a little bit more. What I did here is I used a computer program to plot on the psych chart. The important thing here is dry bulb of 72 degrees. All right. So here is 72 degrees, and I went up to the 50% relative humidity line. Please do that on your chart. And the reason I want you to do this by hand is that I want you to make sure that you know how to use it. All right, so just plot that point. Then read the relative humidity, the relative humidity is 50%. The absolute humidity in grains should be, if you follow this out to the right, it should be right about 59 or 60 grains of moisture. Should be real close to that 59 point. All right, vapor pressure, don't worry about that one. And then enthalpy, all right, dew point and enthalpy and wet bulb. Those are the ones I really want you to read. All right, dew point, once again, take that and go all the way out to the right on your psych chart. Dew point is going to be right about 52 to 53 degrees. Wet bulb temperature, come up this way. Read wet bulb temperature, it should be right about 60. And then enthalpy, if you go past the saturation line to those axes that are out here, enthalpy should be around 18.8. Here's a tip to get the enthalpy correct. On your psych chart, there's an enthalpy line out here and then also along the bottom. What this is meant to do is that if you put a long ruler across there, if you've lined that ruler up correctly, it'll be on the same enthalpy line up here and down here. Try it, right? It's important that you get the enthalpy correct, because when you're doing problems, the enthalpy, if we're looking at sensible load, latent load, and then total load, and you also use the 4.5 times the CFM times the difference in enthalpy to get your total coil load, the easiest thing to read wrong on this chart is enthalpy. So please try that. Now, something important here, you'll notice the dew point temperature is right about 52 to 53 degrees at 72 degrees Fahrenheit, 50% relative humidity. Therefore, if we are using a 55 degree supply air, that diffuser that's on the ceiling won't drip. That's how we get to that 55 degree supply air point. All right, now let's go down to the next slide. Once again, please get your chart and do this manually. All right, let's do 95 degrees dry bulb, okay, right here, 95 degrees dry bulb, and once again, 50% relative humidity. All right, I realize when I put that point on there, it was just a little bit off of that relative humidity line. All right, but it's supposed to be 95 degrees Fahrenheit, 50% relative humidity. Notice the absolute humidity is 127 grains. Remember just that last slide where we had 50% relative humidity and 72 degrees Fahrenheit. Absolute humidity was only 59 grains. You double the humidity in the air going from 72 degrees to 95 degrees, even if you keep the same relative humidity. Look at that dew point temperature now. If we take this point, go all the way out to the right, past the absolute humidity line to the dew point, you should find a dew point of about 74 degrees, maybe 75 degrees. It'll be real close in there. 75 degree dew point is tropical. Also note, 95 degrees Fahrenheit and 50% relative humidity isn't that humid for Iowa. It gets worse than that constantly. So we might see a dew point of 74 or 75 or 76. I can remember one day in the summer, not this year, but a few years ago, that we were doing fencing, and it just happened to be a 78-degree dew point. It was absolutely horrible. And then wet bulb up here is going to be right about 79 to 80 degrees. And then enthalpy is 35.17. All right, so find those points on the chart. It's important that you read it. Right? Also notice, and we won't look at what the absolute vapor pressure is, but the important point is that the vapor pressure is much greater here at 95 degrees, 50% relative humidity than it is at 72 degrees and 50% relative humidity, which means every leak and crack and crevice in a building exterior, we are going to have cold air. We're going to have hot and humid air. The vapor is going to sneak in, and then it is going to condense, and that is where we're going to get mold. So sealing up that building exterior is incredibly important, for especially when you're in a state like Iowa that has a whole bunch of humidity. All right, let's go to one more example. This one I did at the end of this Psych Chart. Yours, if you download the big one from the Canvas page, yours goes even colder, but I just took it to 30 degrees, 50% relative humidity. It's not that cold. 30 degrees, 50% relative humidity, that gives you a dew point of 14.5. And look at the grains, absolute humidity, only 11.5 grains. You get colder than 30 degrees, the grains are going to get down like if you look at your chart, if you were to plot 0 degrees Fahrenheit and 50% relative humidity, I think, and I'm going by memory here, which is always dangerous, but I want to say it's like 2 grains or something. It's very, very little moisture. Relative humidity is meaningless without knowing the dry bulb temperature. And 50% relative humidity can be dry, 50% relative humidity can be tropical. It all depends at what dry bulb temperature are you getting that relative humidity reading. All right. So today's, I just wanted to add this little snippet here today. In the announcements, as you've probably seen, there's a few resources there for you to help you. And some of them are pretty good. They're optional reading. I'm just saying that if the way I explain the Psych Chart, if you need a little bit more information on that, or you want to see it in different ways, I strongly suggest that you read through those links that I posted. They're not, they're not testable in that there's nothing in them that you can't find in my lectures. So it's not new material. It's just kind of restating the same things that we've been going through. So go ahead and look through that. And then tomorrow, I want to do a couple of things. Please, 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 please try that homework. I'm going to add another homework here with this one, but try the homework that I've already signed, and be sure you ask questions. If you've got questions, please ask them so that I can let everybody know if I think it's necessary or be helpful to restate that question and tell it to everybody. Put it on the discussion page, also a good idea. All right, so take a look at the homework and stand by for some more lectures on the Psych Chart tomorrow.